This lesson will be about types of forces. We're going to start with the contact and non-contact forces and the most common ways the examiner may ask questions from you, right? Okay, so this is a brief idea what contact and non-contact forces mean. Now we're going to get into the details. The only non-contact force that we're going to get in detail is the gravitational force, and the rest of the contact forces will be discussed in detail in the incoming lessons, right? Okay, starting from a frictional force. What is frictional force? So it is a force that opposes motion. Simple as that. And the only type of energy it releases upon its existence is thermal or heat, right? These are common examples of how and where friction may be visible to you. So if a person tries to push a box in this direction, and the resistance that anyone feels while the object is being moved is called friction, right? You can experience this by rubbing your own hands, the opposition that you feel while moving a chair or moving a heavy object or dragging a bag or a piece of object along a surface or along a rough surface. Whatever resistance an object experiences is basically friction. But for friction, contact is necessary, right? Okay. Now, in this second example, if you see that the object is being moved downwards or it is being dragged downwards, then the friction will be in the opposite direction, right? Let's say if it would have been the other direction, let's say that along the slanting slope, the object was being pushed upwards or it was being dragged upwards. The driving force or the direction of motion was in this direction. What would have happened in that case? So the friction will now be in this direction. So no matter in which direction the object is moving, the friction will always be opposing the motion, right? One more idea behind this is regarding drag. Now, drag, which was previously known as air resistance, is basically a force that looks like or that behaves like friction, but it is for fluids. Now, what are fluids? Fluids are gases, and a common example of gas is object traveling through air. And the second example comes from liquids. The resistance you feel, for example, while moving through water, right? Let's say submarines or boats or any divers, whatever resistance they feel in water or in air is actually called drag. So, for example, if an object is free falling under the influence of gravity, then the opposing force on this object would be drag, again previously known as air resistance. Now, let's say if under the sea there is a submarine that is trying to move in this direction, then it will be experiencing drag in this direction. But if this had been a case in which objects are held on solid surfaces, then we would have called that opposing force as friction, right? Okay. All right. Now, there is a case for forces when it zooms into the tire of a vehicle, right? So the first case will be about acceleration. Let's say that the object is accelerating, right, in this direction. And let's say that the object is trying to brake, but it is still moving in this direction, right? The object is moving in this direction, but it wants to stop. It is going to try to stop. Now, let's see how to decipher this, how to understand this. Now, most definitely, if the object is moving in this direction, then the tire must be rotating in this direction so that the vehicle leaps forward, right? But over here, we'll have to look at it from a different perspective. Let's call this the side left side, and let's call this the right side. And of course, this will be the left side for the second diagram, and this will be the right side for the second diagram, right? Okay, so how do we visualize this force, how it is actually acting? So what's happening is that this green arrow is the force by the tire on the road. So the tire applies a force backwards on the road when this is happening. So this is by the tire on the road. Now, according to Newton's third law, every action has an opposite and equal reaction. So what the road does, it applies a force in the opposite direction to the force applied on the road. So this red vector or red arrow is a force by the road on the tire. So what has happened is that the object has tried to rotate the wheel in this direction, trying to move the ground beneath it to the backwards direction or to the left direction, and as a response of that, the ground has pushed the object forwards. That is how the objects accelerate, or the objects start. Even when we are moving in a specific direction, the moment we start walking, what are we doing with our feet? We are trying to push the ground beneath us backwards, and as a result, the ground pushes us forwards, right? So this is again a manifestation of Newton's third law. Let's look at it in perspective of braking. How does that work? So during braking, the object is moving in the right side or in the right direction. So the tires are already moving in this direction. But if you were to try to stop it, if you want to stop this from happening, if you want to resist it, then most definitely the tires should be rotating or should try to rotate in this direction so that the object stops moving or eventually starts to stop. So what happens is that this is now the force in the forward direction, but who is applying this force? So this force is by the tire, but on the road, right? And as a response to that, as a response to this experience by the road, what the road is going to do is apply an opposite force to this action, right? Now this time this force is by the road on the tire. And this is what we actually observe, that when an object tries to brake or tries to stop while it is moving in this direction, we experience the friction to be in the backwards direction. This is what's happening in that case. And over here, what's happening is that in the acceleration case, the object wants to leap forward. So the friction is actually in the forwards direction. But you have to specifically state that what friction is this. When we ask this question, what we're generally looking for is that this friction was caused by which element and was exerted on which part of the system. Most definitely, this backward direction is also friction. Why are we saying that? Because the nature of the force has to be same according to Newton's third law. And the point of contact that is between the tire and the road, it is only meeting, or you can say it is only in contact with each other in terms of friction. So both are friction, but you have to state specifically that what reference are you making in terms of this friction. Okay, right. Now we move towards gravitational force, and most definitely this is a force acting downwards due to the gravitational attraction of the earth, right? So one common misconception is that the gravitational force is in any direction, whatever feels necessary, whatever feels all right. No, it will be perpendicularly downwards towards the earth. Now what do we mean by perpendicularly downwards? Now let's say that if we zoom out of earth and go into space, if we had an object in this location, and if we had an object in this location, and if we had an object, let's say, in these four locations, if we are standing so far away that the earth looks like this, most definitely we can see that the direction of the weight is going to be in this direction, right? So the direction of weight is this in this direction. Now when we extend it towards the center of the circle, we realize that it has to make an angle of 90 degrees with the surface of the earth while it moves towards the core of the earth, right? This is what we mean by perpendicularly downwards. Now when we draw this in terms of just a single frame of reference, for example, that we see the surface of the earth only as represented over here, that we have zoomed into the surface of the earth, we see an object placed over here, and you see that the weight of the object is being pulled downwards, as it is being explained in this diagram. Now, when we go back to the slanting slope case, for example, that an object is placed on a slanting slope, this is the object, and when a common misconception is asked that to draw the vector of weight, now students generally forget about this, that they think that this is the weight component, because everywhere we draw this is actually downwards, right? But this is wrong. This is going to be the component of the weight. Why? Because if we visualize it with this idea over here, that if this was the surface of our earth, then perpendicularly downwards would be this component and not this one, right? So we are going to remove this. This is the wrong answer, and this, let me draw the correct answer properly. So this is the component of weight of the object, which makes an angle of 90 degrees. Most definitely, sometimes students only draw a small part of it, which is also acceptable. But if you get confused at any stage, you can always extend it to see what's actually happening. Now let's see that it can be put in the rest of the forces that we've already done. So let's say that the object is moving in this direction, right? So the friction will be in the backwards direction because it opposes motion, right? The formula for gravitational force is W equals to mg, and I have a whole lesson explaining how weight and mass work. On the Earth, this is actually 9.8 newtons per kg, or sometimes represented as gravitational acceleration as 9.8 meters per second square, right? Okay. Now we move towards the normal reaction force. What is this force? This is actually a force that generally opposes weight, but not every time, not in all cases. The normal reaction force actually comes from the atoms of a solid surface, right? Now, for example, if this is the tabletop, we draw this in terms of kinetic model of matter, that all solid, liquid, gas states of matter are made out of atoms. And a solid state object looks like this one, right? Now, when you push or when you apply a force on this, there are intermolecular forces between the atoms that are strained because of this. Now, be advised, we are not talking about intermolecular forces. We are not talking about intramolecular forces, which come from chemistry, which are basically the bonds or the type of bonds, which are ionic bond, which are metallic bond, and covalent bond, right? We are not talking about these bonds. We are just talking about intermolecular bonds, which are trying to hold these objects together, right? So this is not what we are discussing right now. These are different forces which are responsible for holding the sizable atoms together, not the atomic ones, but the particles that we can see with our eyes, just like sand and dust, right? Okay. Now, when you apply the force on this, there is going to be a strain on each of these bonds. So I'm going to exaggerate this, but this is not what exactly happens. In an exaggerated state, we see that these atoms actually bend like this because of the weight or the force that has been applied, right? So we can visualize that this is how the shape may change. What happens is that it puts a strain on all of these bonds like a spring, like a sponge, right? So these are, you can imagine them as small springs that are now stretched because of this action. And as a result of that, what happens is that they try to stop this from happening because they are under strain, under stress. So what they do is they apply a counteracting force to this force, which now is known as normal reaction force, right? We represent this as NR generally in my questions, in my diagrams. So this is where the normal reaction actually comes from, the atoms of a solid surface which can support a weight, right? Okay, now in this case the book has some weight and the table is trying to support it by applying a normal reaction in the opposite direction. Now mind you, these are both equal and opposite in direction. The weight, if let's say 20 newtons, then the normal reaction will also be 20 newtons, right? Now we move towards a plank sitting on a slope, for example. The weight of the plank will be from the center of its mass downwards. Again, the idea comes from the Earth's surface, that if you extend it, if you choose to extend it, it should make an angle of 90 degrees with the surface. All right. So now when we move towards the 2 points where there is a contact with the wall and with the surface, with the ground, we have to draw the normal reaction force. Now, another idea underlying this normal reaction is the word normal. Now, normal would mean perpendicular to the surface of contact. Now, how to visualize that in a few examples. Now, over here, if I observe, then the normal or the 90 degrees angle with this surface will be in this direction. So this normal reaction with the wall actually comes out this way by making an angle of 90 degrees with the surface where it is acting. On the other hand, if you observe the floor, this is the floor, the normal reaction at the point of contact will be in this direction by making angles 90 degrees with that respective surface, right? Let's try to discuss a slanting slope case. For example, if we had a slanting slope case like this one again, an object placed in this location, right? Let's say it is being pulled upward, so this is my driving force, then the opposing force will be friction. This will be our weight. I'm drawing a free body diagram in this case for all the forces that we've already read. Now the normal reaction has to be supported or has to act against weight. So what happens is that this is our surface in reference, and since it has to be at 90 degrees, some students consider the normal reaction to be exactly opposite to the weight. The idea or the thought behind it is correct, but the direction of a normal reaction is not going to be this way. It will be in this direction to support the idea that it has to be normal, or it has to be at 90 degrees with the respective surface. So this is our normal reaction in this case, right? Again, a more common misconception. So now this is a free body diagram for all the forces that we have done up to this point, right? Okay, now we move towards tension. Tension is a force that is used to support hanging objects, and it is supplied by generally by rope, thread, and chains, right? This is a force that usually acts against weight if the object is hanging, and acts against a force or tied objects if they are held in this position. For example, if we have a truck that is connected via chains and ropes to a big load at the back end, right? So this will also experience tension. Now this is not exactly acting against weight. So the common misconception in tension is that it always acts against weight. No, it acts against two connected objects and tries to connect them in some manner, right? Now this tension force is acting upwards, but what factor is accounting for this idea? Which action is actually causing for this tension force? So when you apply weight, now this tension actually starts acting, right? So what's actually happening is, now one more point is that tension is always be acting in two directions. It's your job to identify which direction represents what factor. Now let's decipher, let's add this idea into the situation. Now weight, if represented in this thread, is actually acting downwards, but weight is not a part of this rope, it's not a part of this thread. So how is weight being represented to this whole piece of rope? How does the rope know that there is a weight connected to it? So this is transmitted as the form of tension. Now this upwards direction of tension force, which is actually drawn in this diagram, is a representative of a restraining force. But who is restraining it? Who is trying to stop this object from moving down? So that force is actually tension in the upward direction, but this force is coming from the ceiling. The straining force comes from the ceiling. So this tension is a representative of the weight, and this tension component is a representative of the straining force coming from the ceiling. This is the idea that the tension force actually is going to be acting in both directions, right? And they form the Newton's third law pair, most definitely, but collectively. We're not going to say that the weight is going to be a part of that third law pair. No, we can't say that. The nature of force and the direction of magnet should be equal and opposite. In this case, we can see this happening in action as well, right? Now, let's try to explore the case of, in this case, right? So there is a weight, most definitely, of an object, W equals to mg, and there is a tension put on the strain of this system, right? And this is exactly the same idea that we have done in this situation. Now, let's try to discuss the truck and trolley example in detail, right? So for example, this is our truck, its tires, and it is connected by a rope. I'm exaggerating the direction and the size of the rope so that we can fully understand, because there are going to be a lot of forces acting over here. Now most definitely, let's call this object A, and let's call this object B, right? We're not getting into the confusion of truck and trolley. Let's call them A and B. So the object B experiences a backwards direction force, which is friction. And be advised that this is a combination of all the forces. Most definitely the friction is coming from the tires, and the drag is also coming due to the air resistance. So let's call this the force of friction because of B, right? Which is most definitely in the backwards direction, right? So I'm going to call this force as X so that we can label them right now. Now, how does this object A know that there is a load connected back to the backwards side, right? Most definitely this object A is going to experience a backward pull because of the friction components of trolley B. Now how does trolley B tell, now how does object A tell object B How does object B tells trolley or object A that there is going to be some resistance? It communicates this, it tells this object A through this connected thread, right? So how is it going to do that? It is going to represent this friction F component through this chain or through this thread with the force of tension, right? But we know that this tension actually comes from the component of X. This is actually a representative of the friction and drag experienced by B, right? Now let's isolate B for a second over here. Since both objects, let's say, are moving in the left direction, both of them are moving the left direction, how does B know that there is a pulling force on it and it is supposed to move along as well? So B also experiences a forward force coming from the engine of most definitely object A. But how does object A apply this force on object B so that it is catapulted along? Now, it cannot communicate it in any other way other than the connection, other than the thread that is between them that exists over here. So object A is pulling the object B forwards, but it is communicating this with tension that is connected between them. So the forward force of the engine of object A is being communicated to object B through this rope or through this chain because of this and its representative is this tension, right? So the driving force is represented as the forward tension, right? Now, most definitely, if you look at option A as well, or object A as well, what's happening to the object A? So this, let's say that this is the force of engine from object A, and most definitely object A has its own friction, has its own set of drag. Let's call them as Y, right? Now, if you were to draw a second law idea on this, for example, F equals to ma to find acceleration, how would we actually put in these forces? So Fe will be the force of engine, that is the sole proprietor of the whole system, right? Minus the component of Y, the opposition experienced by A itself, minus this X, because the engine has to put up with this load as well, equal to mass into acceleration of the whole system wherever this object is trying to accelerate, right? Okay, so this is the truck trolley example, manifestation of tension. Now observe one more thing again, that tension again came out in both directions through the thread, right? One of the tension is going to be representative of something else and one of them is going to be representative of something else, but rest assured it will be in both directions. It is your job to identify which one is representative of which factor. And then we have this falling mass example, right? We will try to write down a simple equation for this so that we can figure out the acceleration of this block. Now, most definitely this is an analogous example of a certain situation in which we have a trolley like this and we have an object connected in this side and an object connected on this side. Let's say that mass m1 and m2, mass m2 is greater. When you release them, mass m2 will fall down and m1 will rise up, right? So similar idea is being implemented over here as well. Most definitely we can see that the tension forces in both directions, this one and this one, you can see, right? One of them is towards the left, towards the right side, and one of them extended is towards the left side. Now we're going to identify which one is responsible for which factor. Okay, now this tension force, this one is actually a representative of this weight, that is mg, which is trying to pull the whole system downwards, right? And let's look at the other form of tension. What is this a representative of? What is this component of tension representing? Now this upwards tension component is a representative of this block's friction, right? So it is representing the friction, because if we look at it, this M2 is trying to pull the system downwards and it is experiencing an upwards resistive force communicated through the tension, through the rope, through the thread. And who generated that? It was being generated due to the friction between mass M1 and the block and the surface of the table, right? Now let's assume that there was no friction in this situation. Then how would this situation, how would this actually come into being? So we're going to apply F equals to ma. Now let's look at the idea that what factors are trying to move the system. We understand that M2 is trying to move it, so the weight M2G will be the pulling force or the pulling factor minus the friction that is trying to stop this object from moving, which is coming from the other object, right? So this will actually come over here as F equals to, now mass is interesting, we will discuss that later, and acceleration is what we're trying to find out, so it stays as it is. Now what should we put in terms of mass? Now mass is the total mass of the whole system. You see, this is the resultant force that is available for this acceleration in this mass. Now who is moving throughout the system? If this moves downwards, this moves towards the right side. So in turn, both of these masses are connected. So this M will not be the mass of M2, will not be the mass of N1, rather a combination of both masses, because both of the masses are utilizing this resultant force to finally start moving. Because if this friction force was too high and the pulling force was less, then the whole system would be jam-packed and they wouldn't move. If they are moving right now, that means that both blocks are actually utilizing this resultant force to observe an acceleration A eventually, right? That is all for today.